Okay, this is video lesson 5.2. We're going to talk about quantum theory and the atom. Okay, so the wave-like property, the main idea here is the wave-like properties of electrons help relate atomic emission spectrum, tell us what that is, energy states of atoms, and atomic orbitals. Okay, but a scientist named Bohr correctly predicted the frequency lines in hydrogen's atomic emission spectrum. So those are the lines, those visible lines, where we can see that hydrogen only emitted light in certain specific spectrums, not a continuous spectrum of light, but only light in certain wavelengths. Okay, and the lowest allowable energy state of an atom is called its ground state. When an atom gains energy, it's in an excited state. Okay, we're talking about the electrons of the atoms. When they have their lowest allowable energy is the ground state. When the energy gets added to them, they become excited, enter an excited state. What Bohr did was to explain this phenomenon of these spectrum lines, was suggested electrons move around the nucleus in only certain allowed circular orbits. So normally the electron would be at the closest orbit here, a lower energy level, a ground state. But when it got added, energy got added to it, it would jump up to an excited state. And when it lost that energy and came back down to its normal state, it would emit a photon of energy. And that's what we would see as light, that photon of energy. Each of these orbits was given a quantum number 1 through 7. Hydrogen's ground state, of course, is 1. And when an energy level is added, it jumps up to 2 or 3 or whatever. However much energy added, it can go up as high as whatever energy there is. This little video thing I'm going to play here shows kind of a stair-step analogy of how this quantized energy works in an atom. And this shows the ultraviolet series of energy drops. This is showing dropping from an excited state to a less excited state. And the Balmer series, the visible series, it drops from higher energy levels to the energy 2, the second one, not all the way down to the first. Okay, so we get that energy drop, it produces visible light in these 4 colors.
An electron, which is in a higher energy level than its ground state, is said to be in an excited state. When an electron moves from a higher state to a lower state, a photon is emitted whose energy is equal to the energy difference between the initial and final states. This principle is illustrated here for an atom through the mechanical analogy of a ball on a staircase. The transitions which produce photons of visible light for the hydrogen atom are referred to as the Balmer series.
Okay, so you can see when it dropped down from 6 to 2 or 5 to 2 or 4 to 2 or 3 to 2, it emitted a certain wavelength of light. Okay, so higher, when it dropped down from a higher energy level to 2, that was a higher energy level, higher light, higher frequency of light, more energy than the red ones. We're going to learn about that in just a second here.
One of the observations confounding atomic scientists in the early 20th century was that an electrically excited element emits light that has a spectrum consisting of discrete lines rather than a continuum of wavelengths. For this to happen, the energy of the element's atoms must be able to change by discrete amounts. Let's see how spectral lines in the visible region of the electromagnetic spectrum arise for the simplest atom, hydrogen. In this thin vertical tube, hydrogen gas has been excited by an electric current. The molecules split into separate H atoms, which absorb electrical energy and then emit light. The spectroscope separates this light into individual wavelengths, which appear as lines in the spectrum. Look through the eyepiece to see the 4 major lines in the visible spectrum of atomic hydrogen. Now we'll explore how they arise. This small bright sphere represents the ground state hydrogen atom. In this most stable state, the atom is in the n equals 1 energy level, and its single electron occupies the 1s orbital. When the atom is excited, and depending on the amount of energy it absorbs, the electron can occupy one of several higher energy orbitals, such as the 2s orbital, the 2p, the 3s, the 3p, the 3d, and so forth. For example, here, a ground state H atom in the gas discharge tube absorbs enough electrical energy for the 1s electron to occupy the 2p orbital. And then, before it emits that energy as light, it absorbs even more energy, and the electron occupies the 4s orbital. Whenever the excited H atom drops to the n equals 2 level, it emits a photon with one of 4 specific wavelengths in the visible range. To see how the 4 spectral lines appear, we'll look at some of the possible transitions from higher energy s orbitals, whose boundaries are indicated by the dashed circles, to the 2p orbital in the center. Many other transitions can occur as well. Now, as the film strip unfolds, watch these photons emerge. The lowest energy transition is from the 3s to the n equals 2 level, and the emission is a photon of red light, which has the longest wavelength. More energy is emitted with the transition from the 4s to the 2p, and it appears as a photon of green light. A still higher energy transition occurs from the 5s to the 2p, and the emission is a photon of blue light. And the highest energy transition occurs from the 6s to the 2p, which appears as a photon of violet light, whose wavelength is the shortest. Lines in other regions of the hydrogen spectrum arise when the excited atom undergoes transitions to other final energy levels. Thus, the ultraviolet lines arise from transitions to the n equals 1 level, and infrared lines from transitions to the n equals 3 level. Only an atom whose energy is quantized, that is, exists in certain discrete amounts, can give rise to spectral lines.
Okay, so those are the spectral lines he's talking about, like going from 3 to 2, 4 to 2, 5, and 6 to 2. Okay. Bohr's model was great for hydrogen, but it failed to explain any other element's lines. The behavior of electrons is still not fully understood, but it's known that they do not move around in circular orbits. Okay, so I think I want to stop the video here and break it into 2 parts.